Hey, welcome back. I'm checking on the live stream, make sure there's video, sound, normal kind of check-in, talking about. Hey, welcome back. Checking on the live. Seems like we're pretty good. So I went through more of homework 3 kind of work, and then also I was reviewing the AI. I don't know, it feels weird to call it conversations because it is a computer, like you're kind of talking to a computer, but like the learning coach sort of interactions, I guess. Interactions is a good way. And there were like 2 main things that I wanted to look a little deeper at based on some of those. One was like the difference between implicit and explicit methods, which is specifically like this, it's introduced in this case for oscillating systems. So we'll take a look at that first. And then the next part was looking at initial value problems with the shooting method. And this is a really great way of solving. It's a great way of like rethinking how you solve problems. So in this case, it's very particular to initial value problems of like, you know the initial state and you know the final state. How do you find a way to get to the correct initial state? Like you only know a piece of it. So we'll take a look at those 2 things for, and I'll kind of, let's talk through this a little bit. So I'll just do like a kernel restart run all. And I want to show, this is an implicit method, this implicit Hün's method. There is an explicit Hün step, but in this case, in this reading, we were looking at this implicit method where the main thing that makes a method implicit is that there's some kind of iterative check where in this case I'm saying like, all right, I need error tolerance to be 10 to the 1, 2, 3, 4, 5, 6, 10 to the negative 6, and I don't want you to use more than 100 function evaluations during the check. And if that relative error, so relative error is like calculating what the value is, subtracting it from the previous value that it was, and then divide by like whatever your best guess is. So in this case, it's the next state, not the old next state. And we're just checking to see what happens there. So let's try. So if I take this and I think we just have like this, a spring mass kind of function in here. I'm just scrolling back up. Sorry to go up and down. Euler Kromer, spring mass, this one. So spring mass is going to give me, I'm just going to say like W equals 2, like that, so I know that it's 2. And then I'll come back down. And here's my Hün step. And let's take a look at that spring mass. Let's say we're 1 meter and we're starting 1 meter away from equilibrium and we're moving 0 meters per second. That means we're going to accelerate at -4. So we stretch the spring, it's gonna pull us back towards 0, but our initial speed is 0. So if this is my initial state and I want to figure out what happens 1/10 of a second later, just 0.1 seconds. I could say, I'm going to call this like y0. And I didn't change anything, I'm just adding some stuff. But I could say y0 plus the change in y0, which is that spring mass value, times dt, gives me that 0.1 seconds later, I'll be moving, I'll still be at 1 meter, but now I'm moving at negative 0.4 meters per second. And the reason for that is that I wasn't moving at time 0, so there's no reason that I would have actually changed position. So it seems like things are working. Now let's take a look at like what this, and that's what this step did, is just adding that state. So now let's take a look at what's happening here whenever I say, all right, so this is why this is going to be my y0 old is that, and now y0 new is going to be that y0. So it's still the same, I'm plugging in the same value of state into the thing. Oh, I don't want to delete it. But now what I want to do is add the average of that spring mass of the current value and spring mass of, oh, I guess really I should call this like y1, right? Like time step 1. And I haven't defined y1 new yet. y1 new is based on y1 old. And I take this whole thing, divide by 2, multiply by that time step. And I'm just printing out, instead of writing out print, I'm just like saying the last thing that I should do. And what I can see is that now there's a small difference. Now it's saying that really I did move. Like during this time step, while I was accelerating, I was probably moving. Like it's probably not the case that I went from 1 meter and then 1.1 seconds later, I'm still at 1 meter. So this is getting like a little, it's filling in the gap between that time 0 and time 0.1. So it's a little bit better. Let's do and then if I do it again, then it's not changing these values very much, but and let's start, maybe we should start printing each step, right? So now I'm taking a look at how things are changing, and I'm getting a better estimate for my new position and a better estimate for my new velocity because I'm iterating on this. And what we saw in this case is that with an implicit method, it there's less error in this case, like especially when there's lots of changes happening. So oscillating systems, or yeah, oscillating is big. And implicit is better for a lot of like finite element solutions too. It's using a little bit more time, like it takes longer to run an implicit method, but for the most part, it's usually better. And all right, so we have this implicit method, it's running. I can look at the results, but let's say that the mass is 1 kilogram. Should comment that. And K is 100 Newton per meter. Or wait, I can't do that. I have to say, so root K over M has to be this W. So W has to be root K over M. So then M is K over M is 2 squared. So if M is 1, K is 4. Yeah, try that. And what I want to do is just create, like look at the energy of these different plots. So the kinetic energy of my Hune is going to be 1/2 times M times num Hune bracket colon 1 squared. The potential energy of Hune is just, 1/2 times K times num Hune colon 0 squared. And I'm going to do my fancy multi-click, and I want to unclick that one, RK2, right? So I have numerical with Hune method, numerical with an X. And the main difference here is implicit versus explicit. They both have the same order of convergence. So if the time step is half the size, I have 1/4 of the error, like error decreased by 1/4, whatever measure of error I'm using. And in this case I can see that energy is not conserved, like something's happening, but I want to see like what that looks like. And how's this? Looks good. So when kinetic energy goes down, potential energy goes up. Nothing too fancy here. Well, let's try this. Oh, get rid of that. So kinetic plus potential is a constant value, at least it should be. But what I'm seeing here is that it keeps increasing even for this Hune method. But when I look at the scale of this, it goes from 0 to maybe 5 times 10 to the negative 5 plus 8. I don't know what the plus 8 is. RK2. And this is what we get for explicit method, is that we keep, and that's kind of what you would expect, right? Like if you have a growing amplitude like this, really what we're saying is that energy is not being conserved. Like something is artificially adding energy to our system, and we can try to fix that. We can say, like, okay, time interval, so dt, let's go down to 100 time intervals per period. Now we have like a lot better convergence. And if I look at this, I still have an increase in energy. It's a lot smaller. Like as I start converging this explicit method, it will get better. I won't keep artificially adding energy to it, but the longer the time span I'm trying to add to it, the more it's going to still be there. Meanwhile, with implicit methods, for the most part, it's always conserving energy because it doesn't move on to the next step unless it converges, like we were showing, like we were working on up here. Like we kept, oh, not there. You keep trying this, you keep saying y old is y new is y old, you keep going back and forth until these numbers reach a certain error of like, okay, they're like this one has already stopped changing after those first two attempts. So that one's okay, and then the next one, just when that one stops changing, then you can move on to the next step. And that's actually a big way of making sure that you don't continually increase your energy in a simulation. Okay, so there's that. And I saw, for some reason, whenever you ask, okay, let me close some of these tabs. And we'll go Copilot. Module 3. Give me an implicit Kuhn step method. I'll zoom in some. So let's see if this one is also using. See, this is what I would expect for implicit methods, is that you have a tolerance and some max iterations, and you keep checking the tolerance. This one's using an absolute like an absolute error instead of a relative error. I was dividing by that y next, or divide by y next, but it doesn't really matter. It just changes it a little bit. So that makes sense. So let's try give me an implicit integration function I can use for an oscillating pendulum. Because sometimes what I see in some of the code is that, okay, so there's our differential equation popping up, implicit. Oh, this one's also using an if. It's checking the tolerance here. That's weird. Because the thing that I keep seeing, it came up more when I was using ChatGPT. give me an implicit Kuhn integration method Yeah, this is what I keep seeing pop up in some people's code, is like some either optimize import root or optimize import fsolve inside this function so that the solution that you get to, instead of looking for convergence, is using this root finding method. And it's just kind of a weird way to do these, to implement these implicit methods. They seem to work. Like I've used them before, and it doesn't seem to make a difference whether I use fsolve or I use a convergence check. I guess the only thing that I worry about in importing this like optimized root and the fsolve is that you have less control over the error that you're looking. Error that you're looking for, you can. There are inputs for that, but the max evaluations, not as much. This one has an extra if statement of like, hey, if you don't end up with an actual solution here, then it'll return an error. Most of the time it works, but it's just kind of weird. It's better to just define your own. At least if you're going to build your own, if you're trying to build from scratch your own integration method, then it's better to actually control, like, all right, what is the state? How am I defining that? How am I updating it? And then what is my comparison method? So in this case, I'm directly saying that it's the relative error between my previously calculated state and my currently calculated state. And that's how I calculate like whether or not I want to break the loop and move on to the next step. When you use fsolve, it has all these other internal things that it's doing to try to solve the problem. But just so you know, if I'm in the homework or upcoming project, if I'm asking you like, hey, why did you use fsolve here? Usually that's why I'm asking. It's like, are you just using it because I told you to, or is there something that you found that is actually better? So far, I haven't found a reason to use fsolve or root. Like they're both kind of the same thing. But this is it. This is the main thing. Every implicit method will have something where it has an iterative correction. So they will all be better at conserving energy. They won't be perfect, because it's still, oh, whoops, not that one. I wanted to comment the next one. It's not going to be perfect, but there's a lot better energy conservation, like total kinetic and potential energy conservation with an implicit method. Yep. So it depends on how long you want to simulate and all that. Okay, so then the next thing was like in this getting to the root. Here, I was trying to think if I should go through this example or if we should start from scratch. So I'm just going to run down. Because in this example, the idea is that we want to simulate these orange dots. And I want to simulate it by using a differential equation, not by taking this information in. I do need to know what the initial position and what the initial velocity is. So I know the initial position because that was measured. I could estimate initial velocity with that, with what we did, like the diff of y over the diff of t. That would give me an estimate. Or I can say, well, I know velocity at time 0.58 seconds, and I know position at 0.58, and I know position at 1.42. Let me just change the velocity until I get the right initial state where my final height is the right height. And let's try that here. So we're using, in this case, we have the same drag equation, like falling with drag. We'll use like this Runge-Kutta 2 method. And now FV. So let's take this stuff out of FV so we can take a look at it. And this Y bounce, let me go grab that data, just so we have everything in one spot. And let's do okay, so T bounce and Y bounce, that's real data from that, from this like high resolution bouncing tennis ball data set. And I'm grabbing at this time, from this time sequence, it hits the ground, flies through the air, and then at 1425 index, it hits the ground again. And that's what we're looking at up here. Is that ground, air, ground. And I want to simulate that whole thing, but not, the only thing I want to use is the fact that its initial height was this, and then its final height at time t was that. So total time span goes from t bounce 0 to t bounce -1. I use 50 steps to get there. So if I'm using 50 steps, then make a lin space from the initial time to the final time. My dt is going to be the difference in those times. Then initialize my solution for this ball that's falling. Then I'll just literally make a guess. A lot of this numerical methods, like we're just creating advanced guess and check methods. And that might seem kind of silly of like, why can't we just invert it and solve it like a normal function? It's like, well, we don't have normal functions. We have like collections of numbers, and those numbers change if we give different inputs, but it's not an actual like function like f equals x squared. Like, yeah, we can take square root of f, and now we know x is square root of f. But in this case, it's like f of 1, 2, 3 is 12, 15, 23. It's like, okay, well, how do I flip that? How do I get it to something else? And that's what we're trying to do with these guess and check methods. All right, so after all that, now I can say PLT plot of T bounce and Y bounce. This is the data that I have, like it's hitting the ground, flies through the air, and then hits the ground. You can even see there's like an extra little data point here and here. I like to have like markers if I have discrete data like this. So it's on the ground, flies through the air, then hits the ground again. Now, with v equals 10, what was my path? Where did things go? So I know that I want to go t solution, and I'm going to go numSol drag, show me every height, and we'll do a black line. So in this case, if the initial velocity was 10 meters per second, it would have flown off the ground, and by the end of the time, it's still climbing. So 10 meters per second is way too fast. It's like, okay, well, that's too fast. So then maybe 1 meter per second is what I want to do. And let me get, there we go. 1 meter per second means that by time the ball actually hit the ground, now we are 3 meters below the ground. So it's as if it fell off a cliff in this simulation. So something's wrong there. And hopefully you're asking yourself, like, well, why aren't you using some kind of root finding method if you know the answer is here and you can define it somehow. And that's what we can do. That's the shooting method. So it's called shooting method because I'm taking shots, right? Like I'm saying the initial slope is this to get to here, and it's wrong. So then I take another shot where I think it's much higher slope, but now that's still wrong. And I have a way to check. If this YT bounce is equal to that last numSol drag, so print YT, print YT minus numSol drag -1 and 0. So in this case, it was supposed to be about 0, but it's actually -2.6. So my error is 2.6. And for that 10 meters per second, my error, it's up at almost 5 meters. It should have been at 0. So my error is -4.6. If I can get this error to 0, then I know what this initial v0 is to match this function. And so this shooting method here, we're using it to do a normal kind of initial value problem. It's just we're missing one initial value. But you can also use it for what's called boundary value problems. Boundary value problem. And let's see if we can find boundary value problem. These are like the boring definitions of boundary value problem. Yeah, vibrations of rectangular membranes, something like this. So for stuff like differential equation, and it happens in heat transfer, in vibrations of solid objects, and like bodies like this. But you know what the boundary conditions are, but you don't know what the derivatives are at those boundary conditions. So one way that you could solve them is with this shooting method, where you keep guessing what the derivatives are. Because if you're solving a second order differential equation, you need 2 initial conditions to solve it. But with a boundary value problem, you don't have 2 initial. You know that this membrane is kind of clamped. And let's open in a new tab. Like, I know that it's clamped all along these edges, but I don't know what the slope is. And maybe the slope isn't even important along the edges. So I could say, okay, what if I know the slope, if I know all the positions along here, and I know them all along here, what's the slope so that they end up back where they started? So anyway, now we can say, all right, well, I can define all these inputs, like here's y0, my time, how many steps I want to use to make this solution, and let's see, when we said the initial speed was 10, we got an error of negative 4.6. FV, I think. 4.6. So in this case, we're just getting the opposite error. A 0 is a 0, though, whether you have a negative or a positive. So we could flip that, but it really doesn't matter because we're trying to get to a 0. So 4.6, still the same error. And we're doing the same steps, like we're solving this thing. We could change this to 100 steps if we're worried about convergence, and it does change it a little bit. And now I could take mod secant of FV, and let's double check. For mod secant, I need the delta x, like how big the step size is to evaluate the derivative. And actually, yeah, let's try that out. For v trial equals np dot linspace of 1 to 10. We know that it's somewhere between 1 and 10. So let's do 11 steps. Can we do 10 steps? 9 steps? There we go. I wanted 1, 2, 3, 4. So I guess I could have done a range, but I like linspace. So 1 to 10, 10 steps. I get 1 through 10, just like that. And what I'm doing is creating I'm gonna tally up all the errors and plot them to see like what's happening here. And what I can see is that at least from this graph, it looks like a straight line. I wonder if that's true. Let's do 20, double it. It does look straight. Looks pretty straight. It's not as interesting as I thought it would be. 1 through 1. What if it's bigger? All right, now it's a little curved. I mean, the answer is somewhere down here, but at least we got some curving to it now. And let's go like -5, like that. All right, so we got a little bit of a curve. Let's copy this. And paste it in here. So on this y-axis, we're looking at what the error is between our model and the actual measured height. And it could be the measured height, or it could be like something, like some kind of fixed value. And then on this axis down here, we have like v guess. And I evaluated like all these velocities. There were only 20 of them, but everything from down here all the way up, I did all those error. I calculated the error for each of them just so I could get a sense of like where things are happening, like what's happening here. So if my initial guess was like we're moving 50 meters per second, then I'm way off. Like I should have been like down here at 0, but instead I'm up here at like 25. So a big error. So I would know somehow I need to move down, like get the error to decrease. What we can do with mod secant is, so if this is my initial guess, I'll take these two delta x terms and evaluate two more function, well, I guess it's not really all we need is just one delta x, right? Just in one direction. So I have one function. I know it's, let's say it's 25. And then I move over delta x. So now I'm at 50, maybe 50.1. And when I do that, now this value changes to 26. So my error went from 25 to 26. So it increased if I go delta x to the right. But I also know how much it increased by. Like I know the slope. And if we were using Newton-Raphson method, then we need the actual derivative. But in this case, I don't need the actual derivative. I'll just use this approximate one and solve for, all right, if this was a straight line, where would I end up? I would end up somewhere down here at like -1. And then I can do the same thing. So this is my new guess. Put dots, move over by that delta x amount to this new delta. And then I find out that the error increased, which is what I want. So I'll end up like somewhere over here. Seems pretty cool. And then I don't have to evaluate everything. So one of the methods we looked at for these root finding was called bracketing. At least one class. There were two classes of methods in this reading. One was the class of open methods, so modified secant and Newton-Raphson. Those are both fast and open methods. If things go well, they're the fastest way to get to the root of the function. The bisection method and this, so bisection and the bracketing method, those are both closed. They will not look for zeros outside of a given range of whatever you give it. And they are slower, but they always find, if there's a zero, they will always find it. But Newton-Raphson, modified secant, they can diverge on their problems. Okay, so we have mod secant. We need to input. Where was I trying to do that? Let's do it right here. I need to give it the function, the step size, I'll try 0.01, and some initial value. Based on here, like it's not going up and back down or anything, and the slope isn't getting close to 0. So I could try 50. it's pretty wrong, but that's okay. And I end up with 4.17, and then these other outputs are how many steps it took. So this is the number of steps it took to get to this solution of 4.2 meters per second. This is the absolute error. So it was supposed to be 0, but instead it's negative 2.5. And then this is that relative error, like in order to get there. Or no, this is the function evaluation, like f of this one. So if I take this value and plug it in here, I get this, yeah. So this is the actual value, and then this is the error that we ended up with, or maybe that's a relative error. Anyway, value error, main thing is kind of like how many iterations did it take. Mod secant, Newton-Raphson, it's usually very quick. 4, sometimes 7, but very fast methods. So it seems like we did a good job. We can take but the proof is always in the pudding. So that means I want to take that initial value, plug it in here, and see that black line fall on top of those blue dots. And sure enough, it's right on top of it. It's exactly what we thought it would be. In the homework, we were looking at the next bounce. Let's see. Yeah, so here 1430 through 2051. Like this last bounce. And so if I wanted to do that one, oh wait, homework, trying to get to the homework again. So instead of going 580 to 1425, I'm doing IO to IE. And fall drag not defined. What? Oh, because I haven't copied it over. I forgot I was in the homework. All right, so we need fall drag. We'll bring that over to homework 3. And now that initial guess of 4.18 meters per second, I ended up with this error. That makes sense because after the bounce, it should have less speed. Whew. And here I do ask you to use that mod secant, just because I want you to at least see these methods. Like it's not that I want you to be able to build your own modified secant method from scratch. But I do want you to at least kind of like copy it in, see how long it is, like how long is this code, what is it doing, like, and some of this might not make sense, especially the first couple of times that you're looking at it. But like in here, in our Newton-Raphson method, we're using an actual like derivative of a function. In this case, we're taking a finite difference derivative of this function to figure out where the 0 is. But we're using the exact same equation that a Newton-Raphson method uses. The only thing that we changed was how we calculate that derivative. So now it's all numerical. Everything is based on how well we can evaluate that function. Yeah, and here's that EA is the final error that we get. So it's got to be less than this number, because then it can actually break. And then there's this extra if statement of like, if XR is actually 0, then use this evaluation of just, all right, just use the absolute error rather than a relative error. So I have that now. Let's find that mod secant of FV. I'll use like 0.1. I'll plug in like 20 just to see what happens. And I end up with this value of like 3.04. And after 3 iterations, even though I was way off, like it should have been moving a lot faster since I knew it was slower than 4 meters per second, but it's still going to get me to the right answer. Yeah, and some people were talking about like how Newton-Raphson, maybe it doesn't converge if it's too far away from an answer. But I think whether it's 100 or even 1,000, 1,000, all right, so 1,000 we start to get the wrong answer. And that part, there's probably something else happening. At 1,000 meters per second, we're basically doing constant velocity over that small piece of time. Yeah, I'm surprised it doesn't get back down there. But let's see, 500. So the distance kind of matters. Like you'll use more iterations if your initial guess is farther away. We don't really care as the engineers kind of using this tool. If you're trying to optimize things, and maybe you want always an initial guess closer, but yeah, there is a factor of distance, but the distance is not so much that it's a problem that the answer is far away. It's more a problem that the function changes along the way. Because if this was a straight line in one iteration, no matter how far away I am, it will always give me the right answer. So just as a proof, let's say y is lambda x 2 times x plus 3. If I want to know the root of y, like what is x when y is 0, well, I can figure that out. I can move this over. So now y is 0, 2x is 3. Let's do 3x. Mod secant of y. We can use any value, so 0.1 and let's say 2. And I end up with -1, which is exactly the answer that I would have gotten. And I got there in 1 iteration. So then let's give an initial guess of 200. It's still -1 in what iteration? Okay, well, let's say 10 million. It's still -1 now in 2 iterations, and both the errors are 0. So if it's an actual straight line, or if it's anything resembling straight line, modified secant is going to be pretty much exact within 2 iterations, 2 to 3, even though you're way off. But it's just those kind of straight line answers are very easy to solve. All right, so that was a lot of talking about how to do these kind of methods, implicit methods, the shooting method, but all like super useful ways of approaching problems that you've probably seen a lot of times in the past. And now hopefully you have like a new way of thinking about it, kind of like inverting the problem, because these are all these kind of problems are inverse problems where you can plug numbers in, get an answer, but what if you want the answer to be something that it's not? Now you have to play around with these numbers until that answer matches what you want. And it's a great skill set to have. So I'm happy to be here kind of helping you develop that skill set. All right, thanks a lot. That's all I had for today. I'm sure I'll be back soon with more talk on initial value problems and integration methods, and we're coming up to July 4th next week, and our project that we're working on is rocket flights, designing like fireworks, doing a little bit of rocket science. Right, it's right on target, right? Cool. All right, enjoy.